Okay, we're going to be looking at some problems off of page 460 from chapter 8. We're going to start by looking at number 10. Number 10 tells you have a population with a mean of 100, a standard deviation of 10, and it's normally distributed. I've sketched a graph of what it looks like. You can notice that about 95%, about 68% of your data is between 90 and 110, and 95% is between 80 and 120, because 95% of your data is within 2 standard deviations of the mean, and practically all of it is within 3 standard deviations. Now, what it's asking here, though, is that is the distribution if you're talking about a single score. So if I'm talking about just an x value, that is what my deviation looks like. But it's asking about sampling distribution. So instead of looking at x values, what I'm going to be looking at here is averages. So the first one says if I have a sample of size 9, what's that going to look like? Well, what we have to do is, first of all, we have to realize that the sample mean is an unbiased estimator of the population mean. So that means if I average all of my sample means together, it's going to equal the population mean. So my mean value is still going to be right here at 100, even if I'm talking about sample means as opposed to individual x values. The variability, though, the whole point of replication is to increase the accuracy of your results, which increased accuracy will decrease variability. So the standard deviation is not just the standard deviation, but it's the standard deviation divided by the square root of n. So in this case, it's going to be 10 divided by square root of 9, which is 10/3, or about 3.3. Now what that means is, now instead of going all the way out to 110 to be a standard deviation, I'm just going to go about 3.3 past, so I'm going to have a standard deviation at about 103, and I'm going to have a standard deviation, the second standard deviation will be about 106, and the third one will be about 109. And the same thing about 3.3, and actually that last one's going to be right about there. Once you have those standard deviations marked, we could sketch the sampling distribution. The total area is still going to be 1. So to keep the area the same, since it's not going to be as wide, it's going to have to be a lot taller of a distribution. So it might go as high as that. So your new distribution is going to look something a lot more like this. And that gives you an idea of what your new sampling distribution would look like. There's a lot less variability, and because there's less variability, you're a lot more likely to get a value right near 100. That's why the height of this sampling distribution of the sample mean is a lot taller than your original sampling distribution. Now, if I chose an even larger sample size, that's going to further reduce my variability. So if n is 15, what I'm going to have to do is I'm going to have to keep going a little bit, and my mean is still going to be right there at 100, because the mean will stay the same. But now my sampling distribution with a sample size of 15, the mean of the sampling distribution, the standard deviation of the sampling distribution of the sample mean is going to be sigma divided by square root of n, so 10 divided by square root of 15. Square root of 15 is just short of 4, so this is going to be about 2.58. That means if I were to sketch this distribution on the same graph, it would be even tighter. So instead of going out to 3 point something, it'd be about 2.5, which means the entire distribution would be a lot tighter in, something like that. So if I were to sketch it once again, it's going to have to be even taller. I don't think I've left myself enough room to draw this great, but it would be even taller and skinnier. And that's the effect of increasing the sample size on this sampling distribution. Now, the assumption I made in drawing this original green graph is that the population, that just shows you what it would look like if the population is normally distributed. But if you'll notice in number 10, it did not actually guarantee that the population is normally distributed. So if the population happens to be normally distributed, that's what it's going to look like, and the sampling distribution would also be normally distributed as well. But what question 11 is getting at is what sample sizes would guarantee that the sampling distribution is normally distributed. So here's what we would be looking at there. If that is my original population distribution, let's say that this is my mean value is roughly there. I had a population distribution looking something like that because it was skewed. What I could do is, if I did a sampling distribution of size 9, it would decrease my sample of size 9, it would decrease my variability. So what you're going to have is it will still be, the average value will still be 100, and as it decreases the variability, you're going to see that hill is getting closer to 100, but it's still going to have some skew. If you continue with the one with size 15, at that point, it's going to continue to pull the center closer to 100, but once again, you're going to continue to see a little bit of skewness on your tail. There comes a point, though, where your sample size gets large enough that it's clustering everything to 100 so nicely that it's going to be just fine. So if we went up to a sample of size 36, what we would probably have at that point is something like this, where the distribution was centered right toward 100, and it would slope off without too much of a tail. Having a hard time drawing this neatly with this tablet, but that gives you the idea of what's happening there. As you continue to increase the sample size and decrease the variability, the center becomes of the sampling distribution becomes closer and closer to the population mean. The median becomes closer to the mean, and that means your data is becoming more normally distributed. So the rule of thumb is generally once your M value gets to be at least 30, it's close enough to approximately normal. If you went a little bit further, if that's what it looked like for 36, if you went an even step further and went all the way to a sample size of 50, you can expect it to be even better. Maybe something on this line for a sample of size 50. Once again, it's hard to draw the distributions that skinny, but it would become more and more closer to normal as N got larger. But on number 11, it would be safe to say for any of the sample sizes 36 or greater, regardless of the original shape of the distribution, your sampling distribution of the sample mean would be normally distributed.